This is part 15 of the series Integration, and in this section we're going to be discovering some of the ideas surrounding something called numerical integration. Now, what numerical integration does is it provides us a way to solve problems through the use of integration without actually having to do an analytical integration or use any of the integration techniques that we've talked about so far. You may encounter things such as partial differential equations that in some cases don't even have analytical solutions or can't be solved analytically. So we need a technique to be able to evaluate integrals without actually having to do an analytical manipulation. And that's what we're going to be talking about today. So we're going to be looking at two different techniques for numerical integration. The first technique is going to be called the trapezoidal rule. As we've learned in this series, the underlying problem that we're trying to solve is to find the area enclosed by the graph of a function. So the area of a curve between some bounding intervals. And with the trapezoidal rule, the way we're going to do that is we're going to improve the accuracy of our area estimate by, instead of using rectangles to enclose the area, we're going to be using trapezoids. And as you can see, these trapezoids fill more of the region under the curve than a representative rectangle would. So a representative rectangle that was circumscribed would have this much more, and a representative rectangle that was inscribed would have this much less. So you can see that a trapezoid in that same region with the same interval would be closer to the approximation of the actual area under the curve. In this session, we're not going to go ahead and derive this formula. I'm going to reserve that for a different session. What we are going to do is explore the practicalities of applying this seemingly formidable expression, which is really not that bad. So let's take a look at what this actually says. If we have a function f that's continuous on the closed interval ab, then the trapezoidal rule is going to be used to approximate the integral from a to b of that function x with respect to x. And it can be given by this expression. So we have an interval from a to b. So it's b minus a over 2n, where n is the number of trapezoids that we're taking the summation across. Now there are two keys to note here in this expression. First is that the first term has no prefix. It has no coefficient. It's just f of x sub 0. And what x sub 0 is simply the x-coordinate of the first interval. So this would be x0, this would be x1, x2, x3, and x sub n when we talk about x sub n. So that's how you would break this up. And the second thing to note is that every term beyond the first and before the last has a coefficient of 2. So your first and last terms have no coefficient, and all the intermediate terms do have a coefficient of 2. And it's as simple as evaluating your function at that x sub 0 value, adding it to 2 times the function evaluated at x sub 1, and so on to the end. And this will provide you an approximate area. In essence, what you're doing is you're using the difference from this to find the height of your trapezoid. And this is base 1, and this is base 2. And if you remember the area of a trapezoid, it's 1/2 the height times base 1 plus base 2. And that's what this formula breaks down to. And we'll see that when we go and derive this expression in another video. Now, as usual, as we saw in our Riemann sums discussions, that as n approaches infinity, as the number of trapezoids increases, our estimate of the area under this curve is going to get increasingly better. Now, the trapezoidal rule is good for relatively rough approximations with very few trapezoids. There is another technique that's similar in nature but has a different background that will give us an even better approximation than using trapezoids, and that is called Simpson's rule. Now what Simpson's rule does is, rather than use trapezoids, it uses second-degree polynomial functions that span the gap between the intervals. And this gives us an even closer approximation to the area under the curve with the same number of rectangles. Now there's a caveat here that we're going to talk about in a second. Simpson's rule starts out very similar to trapezoidal rule in that f must be continuous, a fundamental condition of integrability, and on this closed interval. But here's the caveat. It says let n be an even integer. So the number of our regions must be an even number for Simpson's rule to apply, and you'll see why here in a second. And it has the same approximating value for the integral from a to b of f of x, and it's given by a little bit different expression. Here it's b minus a, the upper limit minus the lower limit, divided by 3n, whereas in trapezoidal rule it was 2n. The first and last terms, just like in trapezoidal rule, have no coefficient, but in the intermediate terms we have an alternate coefficient. We start out with a 4, alternate to a 2, go to a 4, and we end up with a 4. So we start and end with a 4 for our second and our second last term in our sum here. And that's the reason why we have to have an even number, because we have to get these two values in. We have to have a 4 and at least a 2. So there has to be an even number here in order for that to happen. And again, as n approaches infinity, the right-hand side approaches the actual integral from a to b of the function with respect to x. Even though there's not a lot of technical rigor involved in evaluating one of these approximations, we're going to go ahead and evaluate an example just to give you an idea of what's involved and a look at the comparative value of trapezoidal rule with the Simpson's rule. So let's go ahead and do an example. In this example, we're going to use trapezoidal and Simpson's rule to approximate the integral from 0 to pi of sine x dx. We're going to use n is 4 and n is 8 for the number of intervals that we're going to evaluate these things at. So let's go ahead and start with the trapezoidal rule. So we know that the integral from a to b, from 0 to pi of sine x dx is approximately equal to b minus a over 2n. So it's b minus a over 2, and we're going to use the 4 first. 2 times 4, and that's going to be multiplied by the sum of the trapezoidal rule approximation. In order to evaluate this piece, we're going to need to know our x0, our x1, x2, and so on. And that is equivalent to our idea of delta x, which we had before, which is just going to be b minus a over n. And so that's going to give us pi, a is 0, over 4. So each interval is going to have a width of pi over 4. So our first region here is going to be 0, because we're starting at the lower limit a. So we're going to evaluate f at 0 plus, and then remember the intermediate terms all have a coefficient of 2. So it's 2 times f, and the increment is pi over 4, so pi over 4 plus 2 of f at the next increment, which is pi over 2, and then we have another one plus 2f of 3 pi over 4, and we have to have 4 because we're using 4 subintervals. So this is 1, 2, 3. We need one more. So the last one isn't going to have this 2 for a coefficient. So it's plus f of pi because we're at the end. And this is the sum that we're going to evaluate. And our approximation when we evaluate in the calculator is going to be 1.896. So now let's do the sum with 8 terms. So we know that it's going to be this integral, so I'm just going to write the terms. So we have pi, that's b, minus a, over 2 times 8 this time, because 8 is the number of subintervals, times f of 0 plus the second term, f of... Now, we have another calculation here, which is going to be b minus a over 8, which is pi over 8. So that's the subinterval for this guy. So this is going to be pi over 8. And the next term is 2 times f. That's 2 pi over 8, or pi over 4, plus 2 times f of 3 pi over 8, plus 2 times f of 4 pi over 8, or pi over 2, plus f, actually that's 2f of 5 pi over 8, plus 2 times f of 6 pi over 8, or 3 pi over 4, plus 2 times f of 7 pi over 8. Hopefully we're close to the end here. We have 1, 2, 3, 4, 5, 6, 7. We need one more term to have 8 subintervals. So the last one will have no coefficient, or a coefficient of 1, f of pi. And that approximation is going to come out to about 1.974. So by doubling the number of subintervals, we've increased our accuracy, but not appreciably, since the actual value is 2. So let's go ahead and compare this with the Simpson's approximation. For expediency's sake, I've gone ahead and evaluated this, so let's step through this. Simpson's is b minus a over 3n, so this is going to be a 12, times the first term with a 1 for a coefficient, plus the second term with a 4, the third with a 2, a 4, and so on. So it has to start with a 1, end with a 1, it has to have a 4 and a 4 as the second and second from last term, and a 2 in between the terms with a 4 coefficient. So this approximation comes out to 2.005, which is a little bit closer than we've gotten with the trapezoidal rule with double the subintervals. So with half the subintervals for Simpson's, we've gotten a closer approximation than we got with twice the number of subintervals with the trapezoidal rule. So it's a better approximation. And if we look at the result we get with 8 subintervals, we get it to 4 decimal place accuracy. And in actual practice, most numerical approximations, numerical solutions to differential equations that require integration, are done on computer. So with very little energy, you can, in a very short period of time, get a very close approximation using these numerical solutions, which negate the need for doing the analytical solutions. But in cases where you can't get an analytical solution, these solutions are ideal. You may encounter other methods for numerical integration, but the important thing to understand is that we can evaluate integrals without the need to do analytical algebra. And that is numerical integration.